Hello, this is Mr. White, and this video is on the second derivative test. And here's the one exercise that we'll cover in this video. Before we get into that though, let's take a quick look at this flow chart, which I've presumably already shown you in class, and I'm certainly not going to go over it in excruciating detail here, but let's at least highlight the main areas that tend to confuse students year after year. So, when we were first started out trying to find extrema, minimum points, maximum points, we learned this first derivative test. And by now, hopefully you're feeling pretty comfortable with it. And we then followed that up by finding inflection points, which are, to be clear, very different from extrema. We then went on to find inflection points. And even though inflection points are different than extrema, the two processes really felt the same, didn't they? The first derivative test and inflection points. Other than the fact that the first derivative test really focuses on just the first derivative, whereas with inflection points we're focusing more on the second derivative. Other than that, the steps and the table we used were the same. So it is totally understandable that, given that this is called the first derivative test over here, it is totally understandable that students would think that this would be called the second derivative test. But it's not. It's understandable, but it's incorrect. The second derivative test has the same objective as the first derivative test. It's for finding extrema. And just to further the confusion, it does have something in common with the first derivative test. Its first one or two steps are the same. You find the first derivative and then the critical numbers, but past that, it's a separate process. So it's worth keeping this flow chart nearby. As you get more experience with these processes, refer to the flow chart and make sure you're keeping everything straight. Okay, let's get back to the example at hand with the second derivative test. So even though this is called the second derivative test, we still start out by finding the first derivative because we're in search of critical numbers, which is where extrema are found, right? So after we find the critical numbers, then we'll go on and utilize the second derivative. All right, so it may look like we have a pretty even choice in finding first derivatives. It may look like it's an equal amount of trouble to just distribute this out. That exponent isn't too big. Some students may prefer to just distribute that out and as opposed to using the product rule, but I'm going to give you an argument for why we want to consider the product rule in this case. Imagine if you just FOILed this out. Q of x is going to be a fifth degree polynomial. It's going to be x cubed, and then here's an x being squared. So there's going to be x to the fifth plus some other stuff. And then when you take the derivative of q, you're going to get 5x to the fourth plus some other stuff. And then you're going to set that equal to 0 or undefined. And then you're going to be faced with the task of having to factor this, because you're going to need to solve that equation. So you need to factor that ugly fourth degree polynomial. And that is nothing pleasant. So based on that, I'm going to make an argument for let's do the product rule, and we'll find that that makes our job a little bit easier. So product rule says that the derivative of q is going to be the second function, 4 minus x quantity squared, times the derivative of the first function, x cubed. That's going to give us 3x squared, plus the first function, x cubed, times the derivative of the second. And hold on, we've got a chain rule coming up here, right? So we'll put a 2, 4 minus x, quantity to the 1 power for emphasis there, times the derivative of that inside 4 minus x, negative 1. Okay? Before we set that equal to 0 or undefined, let's go ahead and start simplifying or factoring this. Let's look for the greatest common factor between these two terms. And I'm referring to this as being one term and this as being another term. And I'm going to say that their greatest common factor looks to be 4 minus x to the 1 power. Even though it's being squared right here, we've only got it to the 1 power there. And then we've got an x squared in there. We've got 3x squared here, and we've got x cubed here. So they both can afford to have an x squared taken out. And then we'll follow that up with some big parentheses. Okay, so what needs to go inside these big parentheses? It looks like first we're going to need a 3 and a 4 minus x. And let's just double check here. That would give us 3x squared, and that's what we had up here, 3x squared. And it would also give us 4 minus x times 4 minus x, and that's what we've got up here. So we're good. Let's keep going. All right, plus, and it looks like we need a negative 2x. And again, let's double check. Negative 2x times x squared will give us negative 2x cubed. And then I've got the 4 minus x hanging out there in the GCF. That takes care of this 4 minus x. So again, we're good here. All right, let's proceed and continue to simplify here. So we've got an x squared and a 4 minus x. And if I just simplify everything inside those big parentheses, I've got a 12 and then a minus 3x and a minus 2x. That's going to give me a 12 minus 5x. And that is the first derivative that I will set equal to 0 or undefined. Now again, this is a polynomial. I'm not really going to get the undefined case here, but it's just a good habit to keep yourself in practice to look for the undefined case. So that factored form is going to yield us our critical numbers very nicely here. I see that this factor is going to give us x equals 0. I see that this factor is going to give us x equals 4. And if you're wondering why I'm putting it over there, it's because I just feel like putting these numbers in numerical order. I'm looking ahead and I see that this is going to give us x equals 12 fifths, which is about 2.4. So again, I wanted to put them in increasing order, 0, 2.4, 4. So let's highlight those. We're going to put them aside for just a moment, and then we're going to come back to them later. But let's go ahead and remind ourselves what we have to do next. So if I bring that process back out onto the board, the second derivative test process, we see that we have found the critical numbers. Now we need to find f double prime of x and then evaluate f double prime of x at each of those critical numbers. So let's go find our second derivative. I'll scroll back up a little bit here so I can see my first derivative, and that's what I need to derive to find the second derivative. But I got a little piece of advice for you here that only comes with experience. It's not obvious. I'm looking at that, or if you're looking at that and thinking, wow, that's going to be ugly to derive, notice that we have 3 expressions that are being multiplied. So that may appear that you have to use the product rule twice. In this case, we've probably gone over that in class before, and it's not, the prettiest of operations. And again, for reasons that I explained earlier, I don't want to just completely distribute this out. But what I'm going to do is I'm going to just partially distribute it. And again, I haven't seen that in any book. This just kind of comes with experience. I'm going to just rewrite that derivative. Again, I'm not deriving it again yet. I'm just rewriting q prime of x, and I'm going to just distribute those first 2 expressions. So I'm going to distribute that and get q prime of x equals 4x squared minus x cubed times 12 minus 5x. And what did that do for me? Now I've just got 2 expressions, and I can just do the product rule once, and then I'll go back and factor it. All right, so product rule once again. Now I'm doing q double prime of x, and that will be the second function, 12 minus 5x, times the derivative of the first, which is going to be 8x minus 3x squared, plus the first, 4x squared minus x cubed, times the derivative of the second, which is going to be negative 5. Now I'm looking at that, and there's not a whole lot in the way of greatest common factors there, is there? We've got these 2 terms, and it looks like the only common factor we really have is an x. We see that we can take an x out of this expression, and we can take an x out of that expression. So let's go ahead and do that. Okay, there we go. And now I'm going to go ahead and distribute these here and combine some like terms. Okay, there it is distributed. Now let's combine the like terms. And we will get x And let's do our quadratic terms first. 15x squared and 5x squared will give us 20x squared. And then we've got minus 36x, minus 40x, minus 20x. That's going to give us minus 96x. And then we'll take that 96 constant up front, plus 96. And largely out of habit, let's go ahead and factor this, although once again, we're going to find that this doesn't factor quite as much as we would like. About all we can do is take the 4 out of these coefficients there, those numbers. So let's bring a 4 to the outside. I will point out I made this problem up, and it is turning out uglier than I had initially hoped, but I'm not turning back now. And that is our second derivative, factored as much as we can. Again, this doesn't really factor. Okay, and if we were setting out to find our points of inflection, if we're looking for points of inflection, this is what we would set equal to 0 or undefined, as we've done in the past, right? But let's keep our mind on what we were setting out to do. We weren't looking for inflection points. We're looking for extrema with the second derivative test. So let's not do that. Let's remind ourselves where we are in the process. So scroll down a little bit here. We have found the critical numbers. We've found the second derivative. Now we need to take those critical numbers that we found earlier and plug them in to that f double prime. And that is going to lead us to conclude, based on the concavity, whether we're dealing with minima or maxima. So let's copy those critical numbers that are highlighted up above, copy them down here, and let's plug each one of those into our q prime of x equation here. Okay, if I plug the 2.4, I'm going to start with 2.4 just for reasons that are only known to me at this time. If I plug that into q double prime of 2.4, I really only care about the sign. It turns out to be negative 46.08. I'm going to admit I used a calculator for that. Yes, I did. But I only care about the sign, so I'm just going to put equals negative. Because remember, the sign is what tells me whether this is concave up or concave down. So the fact that the second derivative is negative is what tells me that the graph is frowning at that point. However, remember, this is a critical number. So again, the first derivative is 0, a horizontal tangent line, but it's concave down due to that negative sign for the second derivative. And that's what tells me that we're dealing with a local maximum. So I can put local max when x is 2.4. And we'll figure out the y value shortly. Okay, let's look at x equals 4 next. If I plug that into my second derivative, q double prime of 4, it turns out I get positive 128. Again, I only care about the sign, so I'll put a positive. And what that's telling me is that for that critical number where the horizontal line or the tangent line is horizontal, it is concave up. So it looks something like that. That means that we have a local minimum. So local minimum when x equals 4. So now we'll see what happens when we plug in x equals 0 into that second derivative. You can look at it, and that one we can actually do pretty easily in your head. You can see that that is going to give me q double prime of 0 equals 0. And do you remember what that means? That means it's inconclusive. That means that the second derivative test kind of failed us here. We don't know. It could be a minimum, it could be a maximum, it could be neither. So what do we do in that case? Let's scroll down a little bit further here. And we've been making some conclusions at the other two critical numbers, but now we have a case where the second derivative test failed us. And so what that means is that we have to go on over and go back to the first derivative test. I have to admit, this example, again, I made it up, and it's not turning out to be the most compelling case to make you want to use the second derivative test. Trust me, sometimes it does go better than this. But that's going to be part of the challenge, too, is learning to tell when is the first derivative test your best option versus when does the second derivative test look attractive. So let's do a scaled down version of the first derivative test. The interval, we're looking for the intervals on either side of x equals 0, that critical number. So our first interval will be from -infinity to 0, and our second interval will be from 0 till the next critical number, 2.4. And I don't need to go any further than that. I don't need to do any more intervals because we already figured out what's going on with these critical numbers. A test value, let's say -1 and 1. We'll plug that into the first derivative. And I just happen to have a convenient form of the first derivative hanging out down here. So if I plug in this test value of -1, -1, -1, -1, -1, I will get positive, because -1 squared would be positive. Positive. This is also going to be positive. So I get a positive number up here. Now if I plug in my other test value of +1 here, 1, 1, 1, 1, I get positive, positive, oh, still positive. So I get another positive. So let's think of what that means for this function. It means that the graph was increasing, kind of leveled off to a zero sloped tangent line, but then it went back to increasing again. The positive and positive meant it was increasing, leveled out, and then went and increased again. So taking a look at that, we see that we don't have any kind of extrema here at this point. So I don't really have to mention it, but just for the record, I'll put, rather than put local min or local max, I'll put no extreme at 0. So if I were to plug all those values back into the original equation, the original q of x, I would have gotten a 0 here. At 2.4, I would have gotten something that comes out to about 35.389. It's a rather ugly decimal. And at 4, we would have gotten 0 as well. And so our final answer, in looking for extrema with the second derivative test, are these extrema here. So hopefully at this point in class, we've covered enough examples where you're not totally horrified by the second derivative test. I would admit, if I were given the choice for this particular one, first derivative test looks like it probably would have been easier from the get-go, but at least you've seen how the second derivative test works. If we want to check that against a calculator solution, here it is. We see no extreme at the origin 0, 0, but we do see our local max and our local min at the points predicted.